Hello, everyone. This is Yiding Feng. I'm a fifth-year PhD student from Northwestern University. My research interests including mechanism design and online matching market. One of the applications of the online matching market is a ride-hailing platform, where there are some riders and drivers, and the platform wants to design matching policy to match the rider with the driver and guarantee good efficiency. One of the interesting questions has been motivated by the fact that recently, lots of ride-hailing platforms have switching their algorithm from match-as-you-go style to batching style, where match-as-you-go style algorithm will treat each rider separately. Once a rider enters the platform, he or she will be matched immediately. While in batch-style algorithm, the rider will be asked to wait for 1 or 2 minutes, and the matching algorithm will match these batches of the rider together. And it has been reported that there is a significant efficiency improvement by switching from match-as-you-go algorithm to batch-style algorithm. And in today's talk, I will talk about our recent work, which studied how to design matching policy for agents coming in batches and guarantees good theoretical efficiency. The title of this paper is Two-Stage Matching and Pricing with Application to Ride-Hailing. This is a joint work with Red from UChicago and Amin from Stanford. First, let's describe the model. And as before, we will illustrate this in the language of ride-hailing. Suppose we are given a bipattern graph, RDE, where we have a set of rider, a set of driver, and an edge from a rider to a driver means those two are capable for each other. In this model, we will assume that the drivers are heterogeneous. In other words, we will assign a weight for each of the driver. You can think it as a car, the type of the car of the driver, or the service quality of the driver. Further, we will partition the rider into two sets. The rider who has already accepted their offer from the platform. So those are corresponding to the rider who need to be matched immediately. And if they are not get matched, they will leave the market. And RP corresponding to the rider who is still in the pending set. You can think them as a rider who just opened the ride-hailing app and enter their location. So the platform knows which driver is capable for them. In other words, knows the edge between RP and D. However, once they observe the offer from the platform, they might be accept their offer and be ready to be matched or leave the market. And we assume that their accepting probability is given exogenously. And now it's ready for us to define our two-stage matching process. So in the first stage, the platform will pick a matching between RA, the rider who has already accepted their offer and are ready to be matched, with the driver. And in the second stage, each rider who are still pending will accept their offer and join RP tilde with probability PI. So RP tilde will be corresponding to a random subset of the pending set. And then the platform will pick a matching between RP tilde and the driver who are left unmatched from the first stage matching. And our goal is to maximize the expected efficiency. In other words, the total weights of the matched drivers. Here, the expectation is taking over the randomness of the matching policy and the randomness of RP tilde. And in order to have a better understanding of this model, let's look at the example on the right-hand side. In this example, we have 5 riders and 5 drivers. So among those 5 riders, the top 3 are in the accepting set, RA, and the bottom 2 are in the pending set. So in the first stage, the platform will pick a matching between RA and D. Suppose we pick those 2 edges. And for the the second top rider, because he has been left unmatched, so he will leave the platform. And once we finalize this matching, we can remove the other edges. And then we move to the second stage. We will first realize the RP tilde. And let's say that only the bottom rider accepts, and it is in the RP tilde. And now let's assume that we pick the edge between this bottom rider to the bottom driver. And we finalize this as a matching M2. And once again, we can remove the other edges. And the efficiency we get is a total weight of the match driver, basically the first driver, the third driver, and the fifth driver. And therefore, the efficiency equals to 9. Our work is closely related to a line of research about online bipartite matching, where riders enter the platform one by one. And once a rider enters the platform, he or she needs to be matched immediately. The algorithm for online bipartite matching corresponds to those match-as-you-go style algorithm. And as we already discussed in the beginning of the talk, the model in this paper captures the possibility of more efficient matching by accumulating the riders and then makes the decision in batches. And another line of research is a two-stage stochastic matching. And in this direction, different stochastic process and objective has been considered. In order to evaluate the performance of an algorithm, we use a standard notion for online algorithm design, which is competitive ratio. Specifically, given an online algorithm alg, we say that its competitive ratio against a benchmark opt is defined as the ratio where we search over all possible two-stage matching instances, and the ratio between the expected efficiency of our algorithm on this instance and over the expected efficiency of the benchmark opt on this instance. And in this paper, we will consider the following two benchmarks. The first one is optimal offline, which is an omniscient policy, which knows the exact realization of the second stage rider, RP tilde. And then it will pick the maximum weighted matching between RA union RP tilde and the driver CFD. And the second benchmark we consider is optimal online. And it's easy to see that once we finalize the matching in the first stage M1, then in the second stage, it is always optimal to pick the maximum weighted matching between RP tilde and the remaining drivers. And therefore, for any online algorithm, the only decision it needs to make is to pick which matching in the first stage. And basically, the optimal online will be the algorithm which will search over all possible matching in the first stage and pick the one which maximizes the expected efficiency. And in the later of the talk, we will see that the optimal online is not polynomial time computable. Now let's discuss the main results of this paper, where we try to identify competitive ratio against both optimal offline and optimal online. We consider both cases of homogeneous driver, where the weights of all drivers equals to 1, or the heterogeneous driver, where drivers have different weights. Let me remind you that lower bound corresponds to identify algorithm with certain competitive ratio, and upper bound suggesting that there does not exist any online algorithm with competitive ratio above that threshold. Based on the results in the literature, we know that for the unweighted driver, there exists algorithm with a competitive ratio 2/3. And for the weighted driver, there exists online algorithm with competitive ratio 1-1/e. And in this paper, we show that when competing with optimal offline, no online algorithm can do better than 3/4. And we match this upper bound by providing an algorithm with exactly 3/4 competitive. And when we shift into the optimal online, we show that we can achieve slightly higher competitive ratio for both unweighted driver case and weighted driver case. And we also show that it is impossible for us to develop polynomial time algorithm which is optimal online. In other words, so we show that the optimal online is f pitas hard. Basically, unless p equals to np, there does not exist fully polynomial time approximation scheme. In other words, if we want to achieve 1 minus epsilon competitive ratio, the running time of that algorithm will not be polynomial in the input size and 1 minus epsilon. And of course, so all our lower bound algorithm are matched by polynomial time algorithm. In the remaining of the talk, I will discuss algorithm hedge, which is 3/4 competitive against optimal offline. And for simplicity, we will only focus on the setting for unweighted driver. And let me first introduce some intuition behind the hedge. Let's start with a thought experiment. Let's suppose that the second stage is chosen by the adversary. In other words, suppose there's no information about the second stage in our algorithm. Our algorithm doesn't know which rider will appear in the second stage or what is the edge connecting to them. In such case, how should our algorithm pick the match in the first stage? Well, if the graph in the first stage is a completed bipartite graph, then it's easy to say that we should pick our first stage matching uniformly at random, such that each driver will be matched with equal probability equals to the number of rider over number of driver. In other words, we want to match the driver as uniform as possible because our algorithm does not have the information about the second stage. However, we can only do this if the first stage graph is a completed bipartite graph. And it is not clear how should we do this for the general bipartite graph. And the main technical component of our hedge algorithm is trying to introduce the following demand balance decomposition, which will help us to identify how should we match as uniform as possible for general bipartite graph. The definition is as follows. So given the bipartite graph in the first stage, basically we have the rider in RA and driver. We want to partition those rider and driver into k different pair, such that first we can define the demand for each pair, which equals to the ratio of the number of rider in this pair divided by number of driver in this pair. And without loss of generality, we can index those pairs such that their demand is weakly increasing. And we want this decomposition to satisfy the following two uniformity property. First property is defined within each pair. So basically we require that there exists a random matching within each pair such that all drivers in this pair will be matched with the probability equals to dk. And second uniformity property is defined across the pair. So basically, we require that there does not exist an edge from our riders in a high demand pair to a driver in a low demand pair. And it's easy to check that if our first stage graph is indeed a completed bipartite graph, then the DB decomposition will leave all the rider and driver as a single pair. The existence of the demand balance decomposition and how to compute it is as follows. We can consider the following convex program, which is defined on the first stage bipartite graph and a function f, which is an arbitrary function that is differentiable, monotone increasing, and strictly convex. So in this convex program, the constraint is a matching constraint, and the objective is try to capture some kind of fairness notion across the driver. Specifically, it's easy to say that by picking proper function f, the objective is equivalent to the Rosean social welfare or the Nash social welfare. And here we have the following technical lemma for the DB decomposition. Let's X star to be the solution of our convex program for an arbitrary strictly convex function f. And now we can define a subgraph which still use the rider and drivers in the first stage, but a subset of edge whose xij star is positive. And then so we can define the partition where each pair of vertices correspond to a connected component in this subgraph. And our technical lemma suggests that the pair induced by this connected component of the subgraph indeed forms a demand balance decomposition. Moreover, those xij star is indeed the probability induced by a random matching which satisfy our uniform property 1. And this technical lemma can be proved by applying the KKT condition of convex programming. Now it's ready for me to present the formal definition of hedge. First, it solves X star as a solution from the convex program we just discussed. Next, we compute a distribution over matching with edge probability equals to X star. In the first stage, it will return a randomized matching M1, follow this distribution. And finally, in the second stage, it will return the maximum matching between RP tilde and the unmatched driver. First, let me remind you that due to the integrality of the bipartite matching polytope, the step 2 is well defined and it is polynomial time computable. And for the setting with weighted driver, we will basically replace the objective function to the weighted version in the convex program. It's important to mention that hedge do not use the information of RP when he makes the decision in the first stage. And in the paper, we show that by combining hedge with a greedy algorithm from submodular maximization, which indeed uses this information, we get improved competitive ratio against optimal online. And the competitive ratio 3/4 of hedge follows the standard primal-dual analysis. Here is the main results of the paper. Thanks for your listening.